Ever wondered if we could just hop across the universe in an instant, bypassing the vast cosmic distances? Today, we explore the intriguing concept of wormholes. These theoretical passages, also known as Einstein-Rosen bridges, have been a staple in popular culture, sparking the imagination of many. They're often depicted as gateways linking points light-years apart, transforming interstellar travel into a cosmic jaunt. Imagine one moment you're admiring the rings of Saturn, the next you're analyzing the atmospheric conditions on a distant exoplanet. Exciting, isn't it? But it's not as simple as stepping through a door. The reality of wormholes, their existence, and their potential for use in space travel are subjects of intense scientific debate. We're not packing our bags for an intergalactic vacation just yet. So, wormholes theoretically provide shortcuts through the universe. But how would this work? Let's delve deeper. The concept of wormholes originates from Einstein's theory of general relativity. This groundbreaking theory, proposed in the early 20th century, revolutionized our understanding of gravity. It depicted gravity not as a force, but as a distortion of space-time caused by mass and energy. But here's where it gets really intriguing. The equations of general relativity also allow for the existence of wormholes, hypothetical bridges or shortcuts through the fabric of space-time. Imagine a sheet of paper. If you're a tiny ant walking across it, the journey from one end to the other can be long. But if you could somehow fold the paper, bringing the two ends together, you'd create a shortcut. That's the basic idea behind wormholes. They are, in essence, a folded piece of the universe, connecting two distant points in space and time. The theory is fascinating, but it's far from being a practical reality. Let's explore why. Creating a wormhole is no simple task. It would require forms of matter and energy that are currently hypothetical. Just imagine trying to piece together a jigsaw puzzle, but half the pieces are invisible, and the other half don't even exist yet. That's the kind of challenge we're talking about here. Firstly, we'd need something called exotic matter or negative energy. Now, this isn't your everyday matter. It's stuff that theoretically could prop open a wormhole, preventing it from collapsing in on itself. But the catch? We've never actually observed this exotic matter. It's purely hypothetical at this point. Then there's the issue of stability. Even if we could conjure up this exotic matter, keeping a wormhole open and stable is a monumental task. It's like trying to hold open a door that's constantly being blown shut by gale-force winds. The challenges are immense, but recent theories in quantum mechanics offer a glimmer of hope. Quantum mechanics, the science of the very small, might hold the key to understanding and possibly creating wormholes. The quantum world is a strange and fascinating place, where particles can exist in multiple places at the same time, and even influence each other instantaneously over vast distances. This phenomenon, known as quantum entanglement, has led some physicists to propose that entangled particles might be connected by tiny wormholes. Recent theories suggest that the fabric of space-time might be teeming with these microscopic wormholes, a notion that is as mind-boggling as it is exciting. However, the challenge lies in detecting these tiny structures, and even more so in figuring out how to enlarge them to a usable size. It's like trying to thread a needle with a spaceship. The quantum world is promising, but there are practical considerations and ethical implications to consider. But who knows? Perhaps one day we might harness the power of quantum mechanics to make science fiction a reality. Even if we could create wormholes, the safety risks, resource requirements, and ethical implications are significant. Imagine the potential dangers of an unstable wormhole. It's like walking on a tightrope made of time and space, where any misstep could lead to unknown consequences. And then there's the question of resources. Creating and maintaining a wormhole would likely require energy on a scale that dwarfs our current consumption. Comparatively, it's like trying to fund a trip to the moon with the change found under your couch cushions. Beyond the practicalities, we must also consider the ethical implications. Who would control these wormholes? Who would have access? Would it be the privileged few or everyone? The potential for misuse is as vast as the universe itself. While the idea of traveling through wormholes is captivating, turning it into reality involves overcoming enormous scientific, technical, and ethical challenges.